Just in time, yeah. Okay. So, hello everyone. Happy to be here. I'm glad to present today our work, Lost in the Deep, Performance Evaluation of Dead Reckoning Techniques in Underwater Environments. My name is Uber Flores, and I'm from the University of Tartu. This work was done in collaboration with University of Madeira in Portugal and University of Helsinki in Finland. So the importance of dead reckoning is quite obvious because we have it in many applications. So we have it in the smartphones, we have it for over cars, and we have it as well on boats. So then we need to look at what are the trajectories that these devices are navigating. And it's very important, this method, because of course it's affordable, meaning low cost, it's lightweight, and it's very energy efficient when compared to what's the alternative, GPS, right? How the reckoning works? Well, we have talked about this in this session a lot, so I just will say that we need 3 parameters to estimate that reckoning. One is the starting point, then we need the change in angle from the trajectory that we are traversing, and then we just need as well the change in distance that we are displacing. If you want to see this, and in this nice figure, you can see how these parameters are extracted. But the question is, well, we use dead reckoning in many of our applications, but then can we use it underwater? Is dead reckoning performance good underwater? Basically, we take it for granted that all technologies can work anywhere, but what about underwater environments? Now with the emergence of underwater applications, we can think on new innovative applications like, for instance, remote operator vehicles, autonomous drones, and scuba divers just performing some explorations. So in this work, our contributions are that we perform a systematic evaluation of dead reckoning techniques. We use 15 different algorithms, and then we analyze the performance underwater. All of these algorithms, they typically work with the extraction of quaternions. So then this means that we have to establish different, comparable testbeds. So another of our contributions here is this testbed that we designed. So we have the testbed on land, and then we extrapolate it underwater. And then based on this testbed, then we provide new insights about whether we can use dead reckoning underwater or not. Of course, for processing all of the information, we had to implement and develop a pipeline for processing all the data, and then we developed this Aeolus position estimation pipeline, which consists on 6 steps. I will go quickly through these steps, but more information can be, of course, it's in detail in our paper. So this, in the first step, we typically just look for a device that can perform the collection of information. In this case, we use the EMU sensor, which contains accelerometer, gyroscope, and magnetometer. And then we just attach this to a LOPI4 microcontroller. And then we use this device because it has many tools for just dealing with the drifts and physical errors of the device. After that, we just perform sensor fusion, meaning that we just combine all of the data, we calculate the quaternions, and then we then compute the attitude estimation, which is just the extraction of the linear acceleration, which is just the removing of the gravity information, because otherwise the information starts to get a lot of error accumulation. And then with this, once we have the linear acceleration derived, then what we do is that we just select a specific frequency for just collecting data with each of these algorithms. We found that 6 Hertz is actually optimal for all of the algorithms, so we rely on this. And then after that, in step 5, we just calculate the displacement estimation, which is just we have the acceleration data, then we integrate this, then we have the velocity, and we have the double integration of the acceleration, we then get the position. So then with that position, then we can use dead reckoning so that we can just look at the trajectories which are transverse. The experiments, so here is where we actually put the testbed together. So on land, it was very easy because we just need a big space, and then we draw these figures that you see in the ground, and then we put some ropes there, and then we embedded the sensor in these scooters, and then we just traverse these draws multiple times, different distances, different magnitudes, so that we can analyze the performance of dead reckoning. Then we also draw some geometrical shapes, square, triangles, and line, and then we saw whether dead reckoning can actually detect this. And the underwater counterpart, it was a little bit more tricky because we cannot use a rope, right? So then what we did is that we developed then a wood structure. We brought it underwater on the boat, and then we put it there, and then two people were holding it while the third person, the third researcher, was having this nice device here that is a acrylic sphere, and inside then you can see that we have the device. And then he was just using and following this wooden structure to then make the figures as well. So the results. So it was expected that that reckoning wouldn't work as well in underwater because, of course, in underwater we have a lot of unpredicted turbulence and oscillating environments, and it's very difficult. But it was very surprising to see that actually the displacement error was lower in underwater when compared with the land. So then, in particular, we saw that the warps, which were squares and were spiral figures, were better underwater than in ground. And this is because in underwater, when you are diving, when you do the kicking and when you are just, doing some trajectories around underwater, the strength is captured better by the sensor. So then here you can see some as well results about attitude estimation. So then you can see for the different 15 algorithms, and as well we can see here that underwater as well has the lesser error when compared with land. So this is very surprising for us. Of course, when we just evaluate these algorithms on land, we use these geometrical shapes, and then you can see here that we provide which algorithms they perform the best for different distances and for different configurations. And it's very surprising as well that none of the algorithms is very stable. It's very volatile, the accuracy information that it provides. So for instance, you can see the line here for 4 meters, the first figure at top, OLEC was the best algorithm, but when you increase this to 8 meters, ROLEC gets better. And when you increase that to 16 meters, FANC gets better. So then there is no a particular algorithm that performs best. So for displacement, depending on the distance, one gets better, and for turns as well, the performance is as well dependent on the distance. But for when we tested our AELOS pipeline for these warps, we can see as well that we have bigger errors. So for instance, we have here the algorithms that perform the best. So for the drawing of squares and for the spiral, the web report and tilt were the best. And then Matwink and Sam, they were the ones that performed the better for the less errors in turns. But when we compare these land results with underwater, then it's very nice to see that you can actually track all the movements, all the navigation, all the trajectories which are the divers or the autonomous devices doing underwater. And then here you can see the spirals and the squares that they are drawn and calculated with our pipeline. And on top, you can see this nice wooden structure, the rectangle that depicts the setup. So then you can see that this it's better when compared with the land counterpart. So in conclusion, we made a systematic evaluation of 15 different algorithms. It was very surprising to see that they perform very well underwater. Of course, the bad part is that in land they are quite volatile. So then you saw that there was a lot of differences when computing the trajectories at different distances. And yeah, we can use underwater with the reckoning underwater with 5% error for displacement and turn. Warp estimations are better captured underwater because of the movements, and the performance of the reckoning is quite volatile. That's our conclusions. Thank you very much.
So I wonder if I'll ask a question. So I wonder if you're went from land to sea, what would you expect to happen if you went from, say, sea to space? Right, this is another place where it's a different mechanics, essentially.
Yeah, I mean, we can have some assumptions. I think it would perform better because you don't have any friction there in space. So then, yeah. sensors will capture better because when you make a movement, there is nothing to, to stop you or to, yeah, so data will be better, I think.